Okay, so let's start by reading out the question. It's given a rigid stem is maintained fixed at one of its end O. It turns around O in a horizontal plane with constant angular speed omega equal v dot. A point like mass m slips without friction on the stem. It is placed at rest at point A such that OA equal A. Find the most natural generalized coordinate and assess the real and generalized forces. Write and solve the Lagrange equation. So basically in the given figure we can see a person holding a rigid stem where one end of the stem, which we describe as point O, is kept fixed and will be the point around which the point like mass m will rotate. The given condition states that the point mass moves without causing any friction along the stem, and we are also given that mass m rotates with a constant angular velocity omega. So let's first start by defining the axis, which will be fixed at point O and from which we will define our generalized coordinates. So now we know that the Lagrangian is equal to Ke minus P, which is kinetic energy minus potential energy. So our first step should be to find the kinetic energy of the given system. However, before we begin solving the problem and write out all the equations, let's just look at the degrees of freedom the point mass m has. I can easily say that once I log the motion of mass m in OA direction, it can still rotate around the axis in a circle. So if I draw out the trajectory the point mass m will take when I log the motion in OA direction, we can easily say that it will make a complete circle where each radius is of same length. However, if I do not log out the motion in OA direction, we can easily see that the mass m will just come out of the stem and follow a projectile motion path. Thus, we can say that the system has 2 degrees of freedom, one along OA and other is the rotation around the z-axis. Another way of looking at this is by defining a polar coordinate systems, where we define phi as the angle between the stem and x-axis and defining rho as distance from point A to point O. Using simple trigonometric identities, we can see the projection of this polar coordinates on x and y axis, which is rho cos phi for x-axis and rho sin phi for y-axis. So let me write down the coordinates for x and y. X equal to rho cos phi and y is equal to rho sin phi. Now let's define a general vector for point mass m and call it as r. So r is equal to x comma y and is equal to rho cos phi comma rho sin phi, where rho and phi are 2 independent coordinates. Now we know that the velocity vector v is defined as the derivative of the position vector. We can write it as rho derivative cos phi minus sin phi derivative phi rho comma derivative of rho sin phi plus rho cos phi derivative of phi. And now if we want to calculate the kinetic energy, we need to find the v square or the velocity square, which is equal to v dot product with v, which is equal to derivative of vector r times derivative of vector r, which is equal to derivative rho cos phi minus sin phi derivative of phi rho whole square plus rho dot sin phi plus rho cos phi phi squared dot. Expanding the above expression, we get the following expression: derivative rho square cos square phi plus sin square phi derivative phi square rho square minus 2 derivative cos phi sin phi derivative phi rho plus rho dot square sin square phi plus rho square cos square phi phi dot square plus 2 rho dot sine phi plus not plus multiplication. Now we can see that the two common terms cancel out, and then we are left with the following expression: rho dot square cos square phi plus rho dot square sine square phi plus sine square phi phi dot square plus rho square cos square phi dot square, which is equal to rho dot square plus rho square phi dot square. Now this is the expression for the velocity square. We know that the kinetic energy is equal to half mv square. So we substitute the v square that we just found into the following formula, and we get the kinetic energy is equal to half m rho dot square plus rho square phi dot square. Since phi dot is equal to omega, we can also write it as half m rho dot square plus rho square omega square. Now we will proceed to the expression of potential energy. The potential energy is equal to 0 with respect to the stem. I repeat, the potential energy is equal to 0 with respect to the stem and not with respect to the ground, and so it's not mgh. Next we proceed with the expression for the generalized force Q, which is also defined as the amount of virtual work done by the force acting on mass m. The only force in this question is the gravity. So the virtual work done by the gravity force is F dot del x, where F is the gravity force and del x is the virtual displacement. But since the gravity is acting perpendicular to the virtual displacement, this force is equal to 0. We can also see it from the figure if we draw out the vectors of gravity and the motion of mass m. Now we are almost done. We just need to find out the required derivatives for the Lagrangian. So these are the 4 derivatives that we need to find out. Let's just copy out what is the Lagrangian. We know that Lagrangian we found is equal to kinetic energy, which is half m rho dot square plus rho square phi dot square, since the potential energy and generalized forces are equal to 0. So let's calculate the first expression, which is just equal to m rho omega square. The second one is 0 because there is no phi in Lagrangian, and the third is m rho dot, and fourth one is m rho square phi dot. Let's just write down the equation for the Lagrangian so that we can substitute the following expressions. So for the coordinates rho, we have the following Lagrangian form: m rho omega square minus m rho double dot is equal to 0. Now for coordinate phi, we can see that the result of substitution gives us minus m rho square phi double dot, which is equal to 0, and which follows that phi double dot is equal to 0. And this verifies the given detail that we had in our question about the angular velocity. It was given in the question that the angular velocity phi dot or omega is constant, and so therefore the derivative of constant is equal to 0. However, now let's look at the first question. First expression gives out a second order ODE whose general solution is given as rho equal to a cos h omega t plus b sin h omega t. Thus, if we assume initial condition as rho at initial time equal to 0 equal to a, which if we see in the figure is the initial position of mass m, if we define it as a, that will be our first initial condition, And the second initial condition will be of the velocity of mass m at time t equal to 0, which is equal to 0 because mass m, if we assume it's not moving, forms the second initial condition. And then substituting this initial condition into the above general solution, we get the particular solution of the expression where a is equal to small a and b is equal to 0, and the particular solution is given as rho equal to a cos h omega t. So that's it for this video. I will just go over the complete solution so that you can just glance over it one more time. And thank you for watching. I hope you learned something and the concept is clear. And I will see you in next video.